The first person that's told me. Yeah, they're a little long. Sorry. So, did you hem yours? Get out of here. Alright, so come over here, please. And you guys come over here, please. Alright. Closer. 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 Alright. Jacob, would you say I'm a patient? Oh, man. You doesn't know that one. Okay. So, I think I have everybody here. Good. Alright, so when you walk into class, the class is going to be set up as a lab. It's going to be really exciting, right? So you're going to be excited, you want to make lots of noise and some horseplay and all that kind of stuff. And so, unlike what Jacob answered, what do you think? Do you think I'm a patient guy? No, I'm not. Right? So my request to you is, don't make me impatient. Okay? So when you see the lab, when the lab is set up, just walk in there. And what you're going to do is you're going to put, all of your backpack stuff up against the bulkheads, right? You know that, right? So I don't trip on it. And then, of course, you'll need, a pencil and your lab paper, and I think you attached the engineering paper. Anybody was absent yesterday? Nobody? Okay, so you all have it. Arrange yourself in lab groups, guys with guys, chicks with chicks, two-man teams. Okay? Got it? Let's go. Do you have like an interview for, is it a mess?
Yes, I do.
When is it? Oh, it's a long time from now.
Where are you supposed to be? Okay. Enjoy your lunch.
Excellent. We don't need to pass out the papers. The outbox today, we'll take care of that on Monday. So people just get in groups. Two-man groups. Johanna, how are things going? They're going pretty good? Good. Carry on. Got a class I'm trying to run. Okay. Josh, could you please take this and put it over there, please? And Valley, would you take that unit there and put it over there? Yeah, you take yourself with it. Okay? Good. All right, so I see one team, two teams are formed. Okay, we've got some progress here. Please go to the other side if you want to use that station so I can see your eyeballs. Alright, so 1, 2, 3, 4, 5, 6. There's another bin over there, so why don't you grab that bin and why don't you, oh, there's a team here, good. Oh, you don't have a team. Nobody wanted to partner with you? Okay, so grab a bin. Okay, good, 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 good. So where's your team? We're not going to have 4-man teams. There's only one bin there, so we can only have.
Oh, can you get another one?
If you want to cook one up, I only have 8. So here's what we're going to do: is Josh, you're now with this team. Go around that side. You guys, that's your station. Okay? Good. All right. So we good to go? Oh, you don't either. Okay, well that's fine. We'll assign you that team. So you're with them, and Madison, you're with these characters right here. Okay. Yeah, just, you can still decide. All right, all right, so you need a chair, right? So, yeah, okay, so what's the experiment we're going to do then? Electrolysis. Electrolysis. And what does lysis mean?
Break apart.
Break apart, right? And then electro means break apart using electricity, right? It's actually a 2-day lab. We're going to have a discussion and kind of set up the lab today. When you come in on Monday, it'll all be here. You will already have done everything, so you don't need anything from me except you just need to put on eyeball protectors and gloves, right? So that's the only thing you need to do. So all we're going to do today is kind of some of the prep. I have a few videos, that sort of stuff that we're going to do. But before I go any further, I need some coffee. That's pretty important for me. All right. Since I have a moment, Johanna, are you good to go, or is she gone? Oh, she left? Okay. All right, so hey guys, what is it that we're breaking apart?
Water.
Water, right? It's made of. Right, and you guys yesterday when we did our prep work, you did the equation, right? And you guys things matter, all that good stuff. So, when we do an experiment, you guys have learned, like before, we didn't do so much in the physics experiments, but we'll do more in chemistry where we have hypothesis statements, right? And this one's kind of weird because we're going to have 3 hypothesis statements. I know, it's kind of weird, but you'll see, because one won't be enough to prove what we're going to do. So, look at the equation that you wrote down. That means you have to look at your engineering paper that you wrote yesterday. And what is it that water is made of? I know it's an obvious question. Go ahead and tell me. Here's last year. What is it? I mean, Arden, what is it? What's water made of? Yeah. It's made of H2O, so it's made of what 2 elements? And what ratio are they made of? Are they made up of? What ratio of the hydrogen to the oxygen is there? Yes? 2 to 1. Okay. So imagine you were Lavoisier before he met his untimely death. How did he die? You guys remember? Guillotine. Guillotine, he got his head chopped off, right? Father of modern chemistry. Right? This guy that married for beauty and for money, and so things were great for him. He used a lot of money to do a lot of chemistry stuff, right? And then, unfortunately, the French Revolution came along. Did you guys do AP World or US World or I mean World History? Yeah, it's like 1791. In '92 was the Terror. That's when he had his head chopped off, which is a shame. But anyways, all right. So imagine you're Lavoisier, and electricity's been discovered for a little bit. He wants to tear apart water by using electricity, right? Who's the guy that kind of is the father of electrical theory, by the way? Anybody know? It's Ben Franklin. Right. He was the toast of Europe, right, in the late 1700s, right? Everybody wanted to be his friend because of all the stuff he did with electricity. So, we know that we're going to tear the water up with hydrogen and oxygen, and turn it and find hydrogen and oxygen. So, how do we start? If we want to prove that that equation is true, because nobody really knew, right? How would we write our hypothesis statement? Hint, the first word is if. So how would we do that? I want to prove that water has a ratio of 2 to 1. How might we do that? What's the very first part in if-then statements? What will we write? The if part is some scientific principle. So what is the principle that we're saying is true in this case here about hydrogen and oxygen? Right. So if the ratio of hydrogen to oxygen was 2 to 1, right? If the ratio of, and that's what you're going to write in your engineering paper, right? If the ratio of hydrogen to oxygen is 2 to 1, okay? And then what's the next word we put? Right. So then, now we've got to think about an experiment that's going to prove that. Okay? All right, so that's kind of tricky. I'm going to show you a few things. Look at your bins. And I think for the first thing we're going to do, electrolysis means tearing apart using what?
Electricity.
So I want you guys to do, on your teams, I want you to build me an 18-volt battery. You have all the equipment there to build an 18-volt battery. We'll come back to the then part in just a minute, okay? Build me an 18-volt battery. Good. And by the way, this I need everybody's eyes on me just for a minute. These can't really hurt you. When I used to teach my robotics students, everybody look at me, please. Turn around, look at me. These can't hurt you. You know how you tell if in charge? Yeah. If you regret putting your tongue on it, it's probably okay. You know what I'm saying? This one's, it's all right. It's not great, right? So I'm not saying you should do that all the time with like big submarine batteries, which are 200 volts. But generally, like a 9-volt battery, Dr. Blake and I, you know, when we're teaching robotics and that kind of stuff, you know, it's kind of, is the battery good? That's what you do. Okay, get to work. Build me an 18-volt battery. By the way, what's the voltage of this battery? All right, guys, get to work. You guys hear what I said? Right? This one, okay? So you're okay taking them out of the bin, and you're going to want to take them out of the bin. Okay? All right, let's see how yours is going. Here. Let's leave these work with these two. The one that alligator. Okay, give it a try. Let's see. Ah, okay. What do you have looked up so far? Beautiful. That's right. All right. So now try another one with another piece that has an alligator on both ends. Okay. Let's see what you have here. All right. So this is pretty good. Now you don't realize this, but when we put a battery in a flashlight, do we put the batteries like head to head? It's like head to tail, right? So we got to do the same thing, head to tail here too. Right? So you want to, so assume this is, what's is this plus or minus? So what do you think you would connect it to? The plus or minus? It's exactly like a flashlight. There, excellent. Excellent. Okay, you built me an 18-volt battery. Since you guys are kind of ahead of everybody else, then go ahead and attach the other two pigtails there. Let's see. Okay, you guys are making your progress here. All right, well, that's fine. So let's look at this. If you now have this, you connect this one to this one. You decide where you put it. Good. Why did you choose that one?
Because the negative and negative.
You know, I feel like. All right. So, no, I'm serious. Nobody really.
It's just 18.
Alright, so now you want to do the same thing here too, right? Positive, negative. That's what we do in flashlights, right? Alright, let's see what we got. Beautiful. Now that you guys are moving ahead, what I want you to do is put the pigtails on the two ends. See these little pigtails? They go on the ends. Right? Let's see yours. Okay, so we're going to disconnect these. Go ahead and disconnect those. Now just use the ones that have That's good. You got a positive and negative. Now, where's the other one? It's to your right, by your hand. Now, I want you to hook that up to this battery here. Okay. And where would you put it there? Good, good. Now, hook up the two pigtails on the end. How you guys doing? All right, let's see what you have here. All right. Oh, yeah. So you have positive and negative, positive and negative. Now, put the two pigtails on the end.
Is it okay if we put these?
No, it's not. No, there's another end that's being put in. This is the other end. Oh, have you noticed that there's an alligator clip on one end? Okay, you guys are doing great. See, you've got positive and negative. And now with these pigtails, we need these pigtails. I want you to connect those onto the two ends. You know you don't connect the pigtails. You don't connect the pigtails. Okay? Let's see what we have. Oh, dang, what's going on here? Woo! Holy crap. Oh, where was this thing connected?
You connected these two together.
So you know you have a short circuit, right? So what we have here is a melted wire. Right? There's a lot of energy in a battery. Right? So I don't want you to close the circuit. I want the two pigtails just hanging loose. So we're going to take this away because this is for our AP chemistry students, right? We're going to leave that over there, all right? So good. Now we have all this. What happened there? Good. You have pause. These are hooked up correctly. These are hooked up correctly. Now hook up the two pigtails. You're not connected. Okay, let me see you guys. Okay. Good job. This is how they have it. So we have okay. All right. Now, everybody has, looks like, successfully built an 18-volt battery. A couple of things to kind of look at. There's a lot of energy in the battery, so I burn myself, which is pretty typical. I told you I get hurt all the time. There's another example of it, right? So you don't want to hook a battery up so that there's no resistance between the positive and negative end. That's called a short circuit. And the electrons, which you'll learn in AP chemistry, really want to go to the other end, to the positive end. And they'll go really fast through copper, right? So that's why we put things like light bulbs in between them, right? Because it takes a lot of energy to light up a light bulb, so you don't hurt the captain first thing. All right, so now we have 18-volt batteries. Good. So that's the electrode part of the license. Right? Now we have the batteries. So let's think about our, to refresh my memory, what's the hypothesis statement we have so far? Then, okay, then. Now, we got to do something with this experiment. Talk among yourselves, okay? And look at the stuff that I've given you, and think about what you might do and how you might structure this experiment so that you could measure this 2-to-1 ratio. Okay? How would you design an experiment using this? Hint, you need water. Okay. And I don't think I'm giving anything away. Where do you think you put the water? In the bean. Right? There's some other things that you'll have to do. Okay, but why don't you talk about it for a couple minutes. Alright? And then we'll talk about how we're going to do this, and then we'll get to our then statement.
And then
How are you going to design an experiment?
Some with these, and there's going to be, we're going to use these with 2 different levels of water. There's going to be 2 different.
That's right. That's part of it. That won't be enough. That's part of it.
Maybe.
You're on. That's part of it. Yeah, and then you got right now. Think about it. There's water in there, and then what do we use the test tubes for? To do what? When they
And then you put cold water around it.
Right, because it's required. But, oh, it's not. It's how you gonna tell how the tires are? Now, so we're trying to find or any gas doesn't have to be. Okay, I'm just looking for shorts. After being burned, I'm now terrified. Okay, all right. All right, so what do you guys have? I need everybody's attention. What are some ideas that people have about how to set up this experiment? Yes, Isaac.
You fill the beaker with water,
There you go.
and you put the these two together in here.
And what do you think will happen when you put those two leads in the wah-wah? What do you think you'll see?
Bubbles.
Well, you won't see much electricity, but you can, if they're charged, like you can see a little bit of sparks like I can see in here, like that, sure, but that's not what this experiment is. What will you see when the electrodes go in the water? Steam. The water's at room temperature, so it's not going to boil, right? What do you think? What's this experiment about? What are we trying to do? We're tearing apart water into hydrogen gas and... Right, so what do you think you might see? Somebody say it. Louder? Gas, yeah, right? So we'll see, how will we see gas in a beaker? How would it manifest as a beaker that's full of water? What would we see? Say it again? Bubbles, right? Right? So we'll see bubbles. Okay, all right, so we'll have the two leads in there, we'll see bubbles. Do you think that both leads are both going to have hydrogen and oxygen mixed in both of those? What do you think? No, what do you think, Marshawn? They're going to be separate. And what do you think one is? And the other? There you go. All right, so we're starting to get it. So we'll put these leads in, and we're going to see, because they're positively and negatively charged, what's going to happen is the oxygen, well, excuse me, water. Is it polar or non-polar, guys? Big time, right? So what happens first, whoa! You won't be able to see it, but they're like, man, there's an electric field on here, you know, how that delta plus and delta minus we did. So they'll do that, and then what happens is they actually literally get pulled apart, right? So we'll see bubbles form. How do we measure? That's a 2-to-1 ratio. If you put it upside down, that's a good idea, so you capture it. So let's say there's water in here, all right? Okay, so there's water in here, but Isaac's partially right in that we put the thing in there, and then of course we can put the lead under there and capture the bubbles, but what's the problem? Will we be able to see hydrogen in here? Because what's in there right now?
Air.
What's in here? Air. So what do we need to be put in here probably? Water. Right, here's the trick. This is the part. Where's the other one? There we go. Okay, so we'll do this, and I'll just, everybody get up and kind of go over on that side. You guys, like, you can stay where you are, and you can, Larissa, you two guys, but everybody else go over there behind Brathwaite and Arden, okay? So here's the trick. I need some help, though. Why don't you go over here? All right. Good job. Okay. I need you guys up in the room. All right. So this is the one trick, right? And it takes a little time to kind of get it, right? All right. So first of all, I'm going to make sure it's full of water because I want it full of water because what do I want to capture inside here? Hydrogen and oxygen, bubbles, right? And also I need it upside down. I need it upside down into the beaker, right? So watch how I do this. This is not science. This is like how to do something. You know, it's like, all right, so watch how I do it. So I put my hand like that, and it's good water, right? Now, a lot of you will be just like me. This is how I did it. You know, I watched Professor Smedley do this in college. I never did this in high school, I don't think, with Sister Marion. But I did do it, you know, in college. And I was going like this, and I was never able to pull it off, right? Because it really is a two-handed thing. Okay, so if you do it like this, then you can immerse your finger below the level of the surface of the water and you're good to go. Get how I do it? Okay, so I want you guys all to do that right now. Okay, it's okay if you make a little mess, no big deal. Who's this? Okay, yeah. Do this yourself. Yeah, next one. There you go, Josh. Yeah. All I ask is you do not have short circuits like this. See how this is connected to that? Please do not connect these like that. Make sure that they're not touching. Notice they make a short circuit. This is touching this. The electrons are leaving this, and you're running down like that. Okay? What was your question now?
Oh, it doesn't matter.
No, there's some extras because kids break them. You just happen to have the extras. So we've already looked at them this morning.
Wow.
All righty. Good. All right. Now, I probably would say, yeah, I could probably live with that bubble that you have here. Yeah, I know. But, you know, since we're trying to get it right, go ahead and try it again. Okay? Right? So, Art, you try one.
I'm disappointed.
John, you can try one. We can go dump it out. You gonna try one, John? I want everybody to kind of try it out. Make sure they know how to do it. Now, that's nice. That's not really going to matter.
I did it incorrectly. It's fine.
Take that one apart. And, you'll have to do it over the sink or it's going to overflow, right?
Okay.
So we want to do that. All right. Nice. Nice job. Nice. Okay. Now, since, hey, you guys that now are done, would you please pour out somewhere between, so you have your water between 1/2 full and 3/4 full? I do need your thing set up. Please fill your test tube. Okay.
How much water?
There you go.
Between 1/2 and
There you
3/4 full.
go. Now you got it. Good job. Okay. All right. You got one, you got two. Okay. Perfect. How you guys doing? Marshawn, you're good. Okay, I need one more. Josh. And how you guys doing over there?
That's fine.
Okay, so those, good, you've done these, and so you both did these, right? Okay, good. I just want to make sure everybody did. You guys both did these, right? Okay. All right. So go ahead and take it out of the bin so I can see it. And how you characters doing over there?
Pick up water.
Okay. Go ahead, or just one. All right, whatever it is you need to do. It might be helpful for you to have a little water in this, so that. Thank you. Thank you. Okay. So go ahead and do that. Fast. Okay. We wouldn't exactly call that fast there, third baseman, or whatever it is, but I'll take it for now. Have you done it? Where is it?
Well, I had a bubble, so you want to...
All right, go ahead and just put one in there. Okay. All right. Very good. Okay. Good. Yeah. watch out, Kelly's kind of crazy with that. I know. Alright, so we good? Alright, so everybody please put your beakers, please, if you, go ahead and put your test tube back in there. Go ahead, Megan, go ahead. Guys, this is the part where I'm not getting very patient. Take it. Okay, take it. Alright, thank you. Awesome. Hey, you everybody looking at me? Okay. Alright, now we have a lab set up where we can capture the hydrogen and the oxygen. You gotta get how we might capture it. Where would the hydrogen and oxygen go? Okay, so I want to get back to that then statement. We now have a battery, big honking battery, and we now have this lab set up with the water and the test tubes. So, what's our if statement? I'm an old man, I forgot. What did we say? If what?
The ratio of hydrogen to oxygen is 2 to 1.
If the ratio of hydrogen to oxygen is 2 to 1, then what do you think we should put on the second half of that? Okay, here's my request. If you, I know it's hard. Let go of it, please. Please put your hands on your laps. I know it's really exciting, okay? But just put your hands on your laps so you just remind yourself, you know, not to touch it because then I get distracted and I've just forgotten what I was going to say. What was it? What was I saying?
If then.
Oh yeah, all right, if then. All right, so we have the then part. So how are we going to prove it's 2 to 1? What is it we're going to do? I know we're going to capture bubbles, but what do you think? Somebody other than Isaac.
You're measuring it.
Marshall, go ahead.
It'll be double with air in one of the tubes.
Right, well, we will say air because, you know, we're chemists, so air is mostly nitrogen and all that kind of nonsense, right? So then, if the hydrogen is, the ratio of hydrogen to oxygen is 2 to 1, then, how would you say it again, Marshall?
It'll be double the hydrogen.
Right, but I need, what is it that we're going to measure? The bubble. The bubble. So we would say that the hydrogen bubble would be what?
Twice as loud.
And how would we measure it? I mean, we don't have a hydrogen bubble meter, do we? What do we have? What is it? Yeah, we have a silver ruler, right? So we can measure the height of one. So the height of the hydrogen bubble should be twice as, so go for it. So the height of the hydrogen bubble should be twice that of the oxygen bubble. Yeah. Oh, yeah, sure, of course. Yeah, that's it. This is a big one, more than you need, but it's fine. Part-time, you're off. Thank you for taking chances and asking a question. Okay. All right. There you go. Yeah, we have some little ones. Oh, here's a little one, the green one. Does anybody need a towel? Yeah. Okay. I'll get you some other ones there. Logan? Oh, okay, yeah. Are we good? All right, good. All right, so somebody, still having a hard time. Yeah, I know. Yeah, just leave them on the table. I know, it's exciting. All right, so, Jack, are you okay?
Yeah.
Okay. All right, so, what did you write? Right.
If the ratio of the hydrogen to oxygen is 2 to 1, then the height of the hydrogen bubble should be twice as big as the other.
Perfect. Okay. Now, we still need 2 more hypothesis statements because how do you know it's hydrogen? How do you know it's oxygen? Yes?
Whichever ends.
Well, that's really good, and we're going to talk about that, but remember, this is, you know, Joe Knucklehead doesn't know anything about chemistry because he's the father of modern chemistry, Lavoisier. So the plus, the minus, the fact that oxygen, you know, he knows nothing about that. Remember, John Dalton's still in high school, right? So how would we know and prove something is hydrogen? Yes, Larissa.
Set it on fire.
Set it on fire, right? So, let's, would you turn on the overhead light? That's that little white thing there. You know, the thing I'm always looking for, the remote? Yeah. Probably it's white. Here's the other one. Oh, here it is. It's hiding underneath. So, who's heard of the Hindenburg? Okay. So, the Hindenburg was this big honking blimp. Well, they didn't call it a blimp. Blimp is actually something else. It was called a Zeppelin, which I think is a German name. It is. It's actually named after a German general or something prior to World War I. Anyways, what's the question? Okay, you guys okay? Okay. Where was I? Oh yeah, Zeppelin. Yeah. So, you can see, here's the picture, and I'll show you the video. This is the Hindenburg, famous Hindenburg. And it had made a whole bunch of transatlantic flights across the Atlantic in the 1930s. It was really the pride of Nazi engineering. This is 1937 or 38, I forget what year it is. You can see the good old swastika there. And it was flying to the United States. It was going to land in Lakehurst, New Jersey. There's a Naval Air Station there. Because we all know the best pilots, are they in the Air Force? No, they're in the Navy Marine Corps, right? Anyway, so they were flying to the Naval Air Station in Lakehurst. And notice this is watching, okay? Alright, so let me click on this little fella.
The ill-fated Hindenburg on her last flight sails over New York. These pictures, made from a Pathé News plane less than 4 hours before the tragedy, show the world's largest airship heading for Lakehurst, New Jersey. Over Newark's famous Auto Skyway, the airship was hailed by thousands who little dreamed it was that final glimpse of the Hindenburg. Inside the silver envelope are 16 separate gas bags, each filled with hydrogen, a highly inflammable gas.
There's the engines, right there. There's 4 of them, 2 on each side, port and starboard.
From the ground, you can see the forward control cabin from which the ship is operated. The windows along the side indicate the location of the passengers' quarters, in which many were carried to a flaming death.
The people only lived here and then there. That's it. The rest of it was just gas bags.
A puny plaything in the mighty grip of fate. It almost seemed as if fate had set the stage for the horrible tragedy. A graceful craft saved the landing field.
Alright, so now they're at the Naval Air Station. And you can see them dumping water. That's what they use for ballast, to make themselves lighter, that sort of thing. You see all the sailors there, just coming in for a landing.
It is settling in spite of all that has been done.
So she was having some problems staying here.
Finally, the landing lines are dropped. About to see the pictures he got when the ship exploded. Those aboard, an airship destroyed in less than half a minute.
Running away. Some people hopped out and they were on fire and hopped out. You see them running away. See that guy there?
Rushing to the rescue, the heroes of the tragedy dashing, heedless of danger to help the injured to safety, while others, beyond help, perish in the flames.
Alright. Great. So there's Hindenburg. Alright, so we're not going to have a big fire like that, but it's the same chemical reaction, right? So, question first of all, I mean, the Germans, you know, they're not stupid, right? Why did they use hydrogen? It's light, right? So these airships, it took nothing to get them up into the air. All you had to have was little motors that then pushed them around once they were in the air. So it was pretty cool. They're made of aluminum, and it's pretty complicated. The engineering is pretty cool. But what's the problem with hydrogen? It's flammable. So everybody's seen the Goodyear blimp or the Fuji blimp or whatever. What's inside those? helium, which is non-flammable, right? Noble gas, doesn't want to bond with anything, it's great. All right, so our second hypothesis statement. If the bubble is made of hydrogen, then and then you guys talk among yourselves and say, what should we put after the word then? Oh, it's totally dry. They're making batteries, chemical batteries. It's pretty fun. So on Monday they have to, I gave them like this kind of experiment. I just give them copper and zinc and chemicals, and they have to make a battery like the light bulb. It's pretty cool. Yes?
You said that was New Jersey?
New Jersey, yes.
So did the Nazis fly from Germany to New Jersey?
Did Nazis fly? I understand
You
the
said it
question.
was German. So
Yeah, it's true. It flew from Berlin, probably.
New Jersey?
Yeah, it was before the war, right? 1937. Yeah. Yeah. So, year after the famous 36 Olympics. Yeah. Yeah.
Why did they use helium?
Oh, great question. Why didn't they use helium? Well, the answer is that they were just, remember Ramsey had just discovered helium where, I mean, we know it was up in the sun, right, by the French guy who saw it, but where was helium first discovered? Uranium mines. And that was the only place they knew where it was, right? And where did the helium come from? What was it? Alphas. It was decayed alphas, right? You know, so there wasn't like a lot of it. It wasn't until later that they discovered some of the gas that was in like natural gas. And a lot of that like it's helium that just bubbled up, and they didn't really know that. And there was no real commercial way to collect it back then. So it was really expensive. Why not use hydrogen? It's cheap. Well, now we know why. Right? Okay. So, what kind of then statements do you think we should have on this thing? Then what? All right. Well, will it catch on fire just spontaneously?
When a lighter.
Right, so we could say it will ignite. That's a fancy word. It's kind of a Ms. Kyle word. It'll ignite, I can have a better one coming up, when exposed to a flame. Right, because hydrogen is flammable, right? So it would ignite when exposed to flame. So that's what we're going to do, is we're going to light this hydrogen and see if it burns. Right? And it's not going to be like hydrogen burn. Sorry, I know you want something really exciting. That's cool. Alright, so what do you think the last part of the last sentence is? Why don't you, somebody read that. Callie, read me your if-then statement for hydrogen just to make sure we're all on the same page.
If the bubble is made of hydrogen, then it will ignite when exposed to it.
Beautiful, beautiful. So we have a lot of flame starters here. It'll be great. Alright, so what about oxygen? How are we going to prove something with oxygen? Now we all know, we learned in elementary school, not to mention my class last semester, we need oxygen for combustion, right? Right. So, but it doesn't burn necessarily, right? So, but it helps things burn, right? So where's my box of matches? Oh, here we go. All right, so I'll give you this thing. So start the sentence with, if the bubble is made of oxygen then, right? We got the science. We know what we're trying to prove. Okay, then, so we know, and you'll see this, that just lighting oxygen, it's not that, how do I say it? There's not much it does, right? Because it just helps the flame burn, right? Ms. Mallard, would you mind turning around, please? Yeah, if you need to, just turn the chair around. All right, so this is not going to work, but something that's pretty cool will work about, because we're not very coordinated and it's very wet. Well, what if we lit a match by the wooden piece of the match, which is called a splint, if you care. And then what would happen, do you think, if I blew it out and stuck it into pure oxygen? It would reignite, wouldn't it? Right? So if we extinguish, hold on, let me do the English right. But if we if we insert an extinguished flame, it should reignite, right? So there's a lot of second floor words on there, right? Like extinguish and reignite. So that's what we'll do is we'll blow out, I have you guys blow out the flame and see if you stick it in the test tube if it reignites. That would mean there must be a lot of oxygen in there that this thing wants to reignite. Unfortunately, there's a lot of water too, so it may not work very well. Okay. All right. How much time do we have, Marissa?
7 minutes.
Perfect. Okay. Yeah.
The bubbles there, and then if we look on the water column, will it stay there?
It'll stay there because it's lighter than the air, and what we'll do is very carefully do it. You'll see what we'll do, and then I'll have you guys light it. You'll see. Okay.
Yeah.
All right. Great question. All right. So let's see. What do I want to do? I want to show you how to get this thing started. Okay. So why don't you guys? You can stay here, you two characters can stay. The rest of you guys go back over here again, off over here. So you see it. Just need to move over this way a little bit. Okay. All right. Okie doke. So when I say stay there, I meant like come towards me, right? I'm sorry. You guys have to like stand up and walk and all that stuff. Okay. All right, good. So guys, so if all of this is true, the first one is we should be able to stick this into the water, and if everything works well, it should start bubbling, but there's no bubbles. You see no bubbles? Okay. So, but what we can do is we can and the reason why is because the water has to be conducting electricity. So we're going to add some sodium hydroxide. You'll be very familiar with this. We use it all the time. The one thing that you guys will do when you show up is that you will use, in fact, why don't you grab me some rubber gloves? Top drawer, keep going, keep going, keep going. Stop. Left hand side, you're doing great. There you go. See them? The AP Chem kids have consumed a lot of them. We're doing great. Okay, thank you. All right. So, and I'm sorry, you guys have these very delicate hands. We're out of smalls, so. All right. So, what we need to do is help it. Did I pour anything in there?
Yes.
Oh, I did. Okay. So let's see what happens now when we stick these guys in now. What do you see happening? Right. You see bubbles, right? And take a guess. If you guys over there, the Jack and your buddies over there, get over here, okay? Because I need you to see this, okay? Because I want to show you on Monday. All right. So, does everybody see the bubbles? Yes. Okay. Take a scientific wild ass guess. Which one do you think is hydrogen? Which one do you think is oxygen? Okay. What do you think, Josh?
The one on my left is hydrogen.
Why do you think that?
It's bubbling.
Yeah. Yeah. So it's gonna, if it's bubbling more, it means it's producing more gas, which means it's probably the hydrogen, right? So how are we gonna catch it? Yeah. So this is the part that's a little tricky, is you have to, kind of lift this thing up and put it down. See how now these things are hooked like this and underneath there like this, so that we can catch it. And then we'll start, and you can see the bubbles are starting to come up here. Some of these bubbles are being lost, and depending on how much you lose and how you bend it and all that kind of stuff, you'll see if you're good at capturing or not. But you see these little bubbles going in there? So on Monday, when you show up, you're just gonna, these things will just be laying here, right? So you have to build your experiment and start the bubbles, right? And then we get to show a video, which I know you're just dying to see, about life on a nuclear submarine, right? You've been asking me this for months now, right? Kidding. Anyways, but on the nuclear submarine, what do we use to make the oxygen? That. Right. In the video I'm going to show you is how they do it. Right. And we're terrified of those machines. Absolutely terrified of them because of the Hindenburg. Right. When a submarine, both submarines that sank in the 1960s, one of the lead theories as to why there was an explosion was the electrolytic oxygen generator blew up. We thought maybe that's what it was. So we fear this more than we fear torpedoes. So that's what we'll do on Monday. So what I need you guys to do now is not make it easy for who? 8th period, right? So I need you to basically disconnect everything, and then I'll see you on Monday. Yeah, always. Just don't make it easy.